up here. So I swapped out ChatGPT with my own little friendly helper here. So I'll just be logging in here. Homemade application, a homemade rack system. So let's sign in with my Google Pal, Firebase, Firestore. So we are in, and we see here we can ask it several different things, and I'll just link it up to my project that is available on for public consummation here. So I'll just add my links here to the different kind of, and let's have Yahoo Finance also. Okay. Yeah, so I think about adding this later on to combining this and this. So give me the latest trending stocks. Okay, I could enhance UI somehow. UI UX. I don't know why it's. Oh, there's a network error. Okay, so let's go into the backend. It's over here. So let's just have a quick look up. I think we have it terminated. Let's try to run it again. Yeah, okay. Let's just see. Why did it terminate? No such file. Okay. Let's just. What is it complaining about? I made some changes to the last day. Okay. Let's just spin it again. Okay. So I just cleaned up my PC and then I removed that library. So let's just activate another version, another VNV. TF metal. And then just try to run the main app. I think it has so one of the packages libraries. So how should we install this one? So we could ask it without accessing this application, but we could just use it for here. So just paste it in. Hopes it gives us a decent response. So it says here, yeah, we're missing that. I just remember TensorFlow install issues. So we can use pip install TensorFlow. That's just what I needed to hear from it. Conda install. Okay, well, let's use Conda. There has some misspellings also. That's not perfect, my model. TensorFlow. And then we'll hopefully get this working. Okay, so meanwhile, we ditched ChatGPT. It's ran out of limits. We will move into move on from the statistical analysis to go into the model building phase. So follow the slides, and we will see here that we use a hybrid deep learning model for numerical and textual data, and then we integrate convolutional layers for feature extraction from the text and dentist layer for numerical data, culminated in a unified representation for the prediction. So what it says that it's aware of that we have different kind of data. We have numerical and textual data. This is not interpreted the same way for the model, but we will use different kind of machine learning models. We have the hybrid deep learning and the CNN for feature extraction. So it will have some, and so it's divided into multiple layers. So we have one layer where we have all the. Let's just go down here. Let's just walk through it. So, and then let's just see if we can get our assistant on here. So help us like elaborate more on what and explain what giving us more. So could you? So for example, here we could ask it here. Could you give image explanation of hybrid deep learning model and CNN. Oh, it's network error again. So let's just run this our model here. And now it's complaining again. So what I will do is we'll just ditch it. And then we will. So should I not use conda but pip? See here if it behaves any differently. Okay, I think it's because it needs a specific version of TensorFlow. And yeah, so I'll just be closing down here, and we'll just rely on the this one. So let's move on here in the tutorial here. So the deep learning libraries we're using is TensorFlow. We're using Keras models for the model. So this is a great library for machine learning and getting quick going for this, and hiding a lot of technical aspects. We'll use the Keras, but sorry, that was sklearn, but the Keras library is I think it's a part of TensorFlow, but was previously a separate library unit. But TensorFlow is the most. It's developed by Google, and it's maintained by Google, and is a widely popular machine learning framework. And we will use input, dense, different kind of functions from these methods. LSTM, long short-term memory. That's good for serial data, serial embeddings, dropouts. We talked about that also. Adding some dropouts to prevent that we get some overfitting and some because we can see we have some noise in the data where we saw the test data, for example, that was highly coherent, correlated somewhere, bidirectional, global max pooling. I'm not sure about that. We could just ask here global max pooling. So you're referring to global max pooling is a type of pooling operation commonly used in convolutional neural networks. That's what we're doing. So it's downsampling techniques that reduces the spatial dimension. So yeah, so you're reducing dimensions. So we have a feature map of A and we have the height and the width and the C, and then global max pooling reduces the features to a single value, 111C, taking the maximum value across all spatial locations. Okay. Let's just go down here, and then we will see load the data here. We have, as we had before, we have split it up here into different data frames, and we have the shape print out. I don't know why I didn't do that, but there were some issues when I ran. I think secondly, so we have some issues here that I think it's something I just tried to run it, and then we didn't have the right path. So and then we'll print it here. So we'll get what we've got before. And actually I have it here, the neural training numerical dataset with different kind of features. Multi-class classification, 100 encoded integers. Yeah. So we need to define the model architecture here, or we at least did that. So we construct this hybrid deep learning model that processes numerical data, convolutional neural layers. So we will define the input of the model here as numerical input. So, and we will decide what kind of shape it should have. It should be accordingly to the number one column in the so it should have as many inputs as this number here, or 7 here. So we're looking for this is 0, this is 1, and then we are naming it as a numerical input, so it knows that. Then we have a layer here. So this now we get down to the machine learning magic, and perhaps I should draw it somehow. But yeah, but this is like a we have the different layers, and then we have the first layer here. So it's densely connected. So it's connected. So you have like a node here. You have an input of these seven inputs, and then we have the first layer, and then we have some more. I think I'll draw it here. So let's just add a slide, and then I will try to visualize it here. So we need 1, 2, 3, 4, 6. So 7 in total, 7 of these. So this kind of information is like the typical what you'll find in all like machine learning videos you will or introductory courses. So, but it's good to recap here. So it's hard to align them all, but I'll just so they'll need to overlap a little bit here. Okay, so we have these 7 different features here from our PCA instead of 14, and they will have some kind of value, and we have some kind of, so they can be decoded into our, again with some kind of key variable to that. But the PCA now consists of these 7, and we don't know really what they are, but they will have to connect to a layer. So we have a layer here, and that layer is connected with some connections in many different ways. And by that I mean like they are connected from this one to that one, from this one to that one, and from this one to this one. So in like they are densely connected, so that will mean that each of these has at least has the connections equivalent to seven times 7 connections, if I have recorded right. So you will have like 7 exponential. So you will like have connections between these. So they will each be connected to all here, and each of these will all have a connection, 7 connections connected to this. That's why it's dense. And then not only 7 of these, but there will be 128 of these. So imagine those are extended like going up and down. So like, and they will have an activation function. They will consist half. So each of these nodes here will have, when they get from, this is the input layer. This is very important. So the input layer, and then we have a hidden layer, and the hidden layer here, and these are represented in the hidden layers, and the hidden layers can also be here. So so it will expand, and until we get to the final output layer. And within these nodes here, we call them nodes, they will be consistent of, they will be halfly split. So they will have both a function. So the node, like it takes numerical input. So it's like you should imagine it like like the real concept is like a synapse. So, and that will get some input from this layer, and it will have a weight. And this weight is dependent on backpropagation, and backpropagation is dependent on what happens here when it gets in here. So it it will be have an activation function that will ensure that we are mapping non-linear relationships correctly, so that we can somehow interpret this non-linearity, because we will have so many different kind of inputs and numbers. So we will ensure the activation function will ensure that we're not getting some values that will scale down to 0 when they are calculated. So it will avoid, because if we have suddenly become 0 when we run through millions and millions of learning, and learning is like going through and back and forth to this and giving new inputs and then updating what is here is the weights that sit here, and the weights will adjust according to what new data comes in here, and then that data will go through each step here to the last output node, and the output node will calculate an error based on the previous nodes, and then, or the expected answer, and then that error will be added, will be times down in the weight to adjust the which type of weighting each of these connections have. So these connections will have a different kind of weights. So so let's like imagine that if the connection is heavy, is big, or has a high number, then the weight will tend to go perhaps that more often that way, based on the previous, of course, node. So it could like so like you get like a more web of different kind of nodes that would run through the inputs in order to calculate an output here. So like running through. So if you see, like a wind blowing through some mountains, you will determine by what kind of velocity, speed it comes in with. Like, what kind of data is it here? That the data here have the mountains seen this kind of wind before? So if it has, it is able to handle this wind very briefly, but if it's some kind of fire wind or something, it will perhaps burn down, or like it's not adjusted to that kind of input or that new. So it will perhaps be hard for us to understand for the mountains that it comes through. Will be hard to absorb it, and therefore it will be perhaps not giving the. It will need to filter out that kind of wind, because we will not need that in the last part of the village at the end of the mountain. Okay, but at least we have some kind of different kind of inputs here, and this is a rough explanation of what happens. And we use some kind of batch normalization. So I will actually, I'm not curious about what it means. It's a layer in Keras that normalizes its input data to have a mean of 0. Standard deviation of 1. So normalizes data's mean of 0. And performance, so it's stability and performance of neural networks. Here's a breakdown of what happening in the code. It's the input tensor to layer, and then we have is a Keras constructor that creates a batch normalization layer. So at the end of the batch, it's called to layer constructor. So during training, the layer computes the mean and standard deviation of the input layer for each batch of inputs. The layer normalizes the input data by subtracting the mean, and dividing by the standard deviation for each batch. So that subtracts the mean. So in order to like better filter out, normalize the data, so you have some kind of Yeah. So the nodes have, so okay, the layer, and then during inference, okay. Yeah, so we normalize, you give it in within a scale, and you can do that. You can subtract the mean, because the mean is, and then you can like compose it more, and then you can the mean and standard of the input, and then divide by the standard deviation. Okay, so you like get it spread out again, so you scale it down, so you like wrap it up, and then pop. So yeah, okay, so it's like packaging more tightly. It reduces some error reduction. During inference, when making predictions, the layer uses the moving average of the mean and standard deviation computed to normalize the input data. Okay. Batch normalization can help in several ways. It introduces the effect of internal covariate shifts, where when the distribution changes, so it can be like, see some data where that's kind of different. It helps stabilize the training process by reducing sensitivity to the scale of the input data. Okay. Convergence and improved performance. That's a good thing. Okay. So let's just add that note. So dropout, that's where we will avoid overfitting, data snooping, as we talked about earlier pre-processing. And here we have another layer that is also densely connected, and we also use the batch normal here in the process, and then we have the dropout here again. So this is so this is the input. And then this is the numerical input, this is the text input. And this is using embeddings instead, and then it has dimensionality of, so we have more numbers, like all kind of numbers here, because it's CNN, so it's like looking in a square, and then it's like mapping out here if you were to pictures. And output dimensionality, so here's the output dimensionality. It operates in a kind of different way than we so now it's looking like a textual, so it's the same kind of data, so it's just represented in numerical data. So then you have the first dimension here, so it reduces, so it has some filters here, so the filters goes through these numbers here, and then it looks for kind of where it makes sense, and then it can easily filter out the needed the meaning of the text here, and then uses the rectifier linear ReLU activation function, which is separate. It's the same as the previous. So it avoids that we're underfitting, or like we're getting some degrading, vanishing gradient descents. So that we are constantly above zero or very low numbers. So because it's multiplying the numbers always, so we need to ensure that if some kind of input or some kind of weight gets zeroed, then it will quickly start multiplying down, and then we will have no weights so that we can usefully use. So that's machine learning. They have shown good effects, and we have this global max pooling, so where it will take the I think the highest number, we had it here actually. Here. Take the feature map, so it has a map of features here and then it takes the maximum value across all spatial locations. So it looks at all the maps we have mapped out here, the word, this makes sense, and then it will extract only the most essential one, that's the maximum values, the essential values here. And then we'll combine that, concatenate those, and then we will have this architecture here. And then we will end up with this sigmoid function. So it's good at, it's like a curve function that goes So it goes up and then that will give us a number output, numerical output, good for decision making somehow, like percentages output. So the activation function will go in, and then it will ensure that it is on a scale here somehow. And then we will use the atom optimizer and the binary cross entropy for loss. So this is how we will optimize the function here. And we'll look at the matrix accuracy and the AOC, area under the curve, for interpreting. So I think we just need to atom optimizer. Briefly, atom optimizer and binary cross entropy. Atom optimizer is a popular stochastic gradient descent, so stochastic. Used in deep learning, it was introduced by Dietrich Kingman and Jimmy Bear, and it is an adaptive learning rate method that adapts the learning rate for each parameter based on the magnitude of the gradient. So it looks at the gradient and it combines the range of two other popular optimization algorithms at the graph. So yeah. And it's fast convergence. Okay, it's good. And this is a loss commonly used for loss function binary classification. It measures the difference between the predicted probability and the true label. So that's what we're doing here. Binary classification. It's a single output node. So here's a more overview here of the architecture. And params, total trainable params, and then we will save that architecture into JSON. So thank you for watching here in the model building. Next, we'll move on to model evaluation. Model interpretation and evaluation. Thank you for watching.